and half of them will be review. Units 1 through 4 cover all of these beautiful topics up here. This is just for your reference. We'll keep going. Unit 5 is 10 of the problems, like I said. Lessons 23 through 26 will have problems on matrices and systems of equations, nonlinear systems of equations, partial fraction decomposition, and finally matrix arithmetic. Here we go. Okay, so problem 1. Use any technique to determine the solution to the following system. Negative 3x plus 5y is equal to 5. 5x minus 5y is equal to 1. So I could turn this into a matrix, or I could use substitution, I could use elimination, any of the techniques that first pop into my mind. The first thing that I see about this equation is that there's a 5y in the top equation and a negative 5y in the bottom equation. So if I were to add them together, I would be able to cancel the 5y's. So I'm going to do that. I'm going to add the first equation to the second equation. So I'm going to add negative 3x plus 5y to the left-hand side and add 5 to the right-hand side. I kind of switched how I'm talking about that. So, and add 5 to that side. Okay, so 5x plus negative 3x is equal to 2x. Negative 5y plus 5y is equal to 0y. I'm going to write it just for fun. And on the other side of the equal sign, 1 plus 5 is equal to 6. Okay, 2x is equal to 6. That tells me that x, I divide both sides by 2, x is equal to 3. Okay, now I can plug this in. Because I have one of the variables isolated by itself, I can use that information, plug it back into the system. Either one of the equations will work. I pick the top one. So negative 3 multiplied by 3 plus 5y is equal to 5. That's what I know so far. The reason I put it in there is because I want to know what y is, what y can be equal to. So I'm going to simplify this out. Negative 3 times 3 is 9 plus 5y is equal to 5. Add 9 to both sides. 5y is equal to 14. And if I divide both sides by 5, y is equal to 14 over 5. So here I found myself the x value and the y value that satisfy both equations. If I wanted to check my work, I could. I can plug in 3 for x into the second equation and 14 over 5 for y into the second equation, and I'll get the answer is equal to 1. That's one of the ways that I can know that I've got the right answer. I did all my arithmetic right, is if my answer truly does satisfy both equations. So 5 times 3 is 15, minus 14 equals 1. So we did great. Okay, so that's our little solution. And it is a point. It is x input of 3, 14 over 5 is the y value. Okay. Next, we're going to talk about systems of equations with matrices.
Okay, so we can represent these equations with a matrix. Hopefully we're familiar with that. And then we can use reduced row echelon on a matrix to highlight solutions to the system. So if the bottom row of all, so we'll have a matrix C that looks like this, and then once we run reduced row, if it looks something like this, where the bottom row is all zeros, then this one right here is inconsistent. If there's a 1 and something else, then it's independent, and yeah. So anyway, if you see something like this, you have a dependent system. If you see something like this, then we have an answer. Yeah.
So when the whole bottom row is zeros and it's dependent, what is that really saying?
Basically,
because I get inconsistent, but where it's all zeros, I'm not exactly sure.
So when they're dependent, it's basically saying, correct me if I'm wrong, they're basically the same line.
Okay. So instead of like a point, they're like the whole line is crossing.
Right.
Okay.
So dependent, yeah, like there's overlap of more than a single point. So
Right.
there's infinitely many points in there. It might be an entire line, or it might be like a section of a line. I think that's possible as well, but there's infinitely many solutions.
Cool. All right, so we have a matrix right here, and then it has the following reduced row echelon form. So we have to answer, is this system independent, dependent, or inconsistent? And I'll go ahead and say, I see a 1, 1, 1 right here. So I would say this is an independent matrix. So that's as simple as it gets, but it's just knowing our three different cases. So if we see the bottom row is all zeros, then the system's dependent. If it's zeros except for the last entry, then we're inconsistent. So it's just knowing your three options. Okay, part 2. So now we have to use the reduced row echelon form to solve for x, y, and z. Okay, so what this is saying is that z is equal to 1 in this case, where this and this are
Zero.
how to explain? Yes.
So each column represents a variable.
Right, so this column represents the x's, this column represents the y's, and this column represents the z's. So in this case, I'm like so freaking
I get nervous too.
no, like I don't know how to do the math. Yeah, I
Oh.
do, but like
You got it. So the bottom row tells me I've got 0x plus 0y plus 1z is equal to 1. Because that far right column is like the other side of the equal sign.
Right. You'd have a line there for your
So,
augmented
yeah.
matrix. Okay.
This is an augmented matrix. We just didn't put the line because you don't have to.
yeah, so there's a line right here.
Mhm.
So then I have z is equal to 1.
Yes. Yeah. So you see those first three columns correspond to 0 plus 0 plus 1, and then equals 1. The second one on the last row is how I know that z is equal to 1.
You just want to explain this one?
Sure, I got you. I can switch. So this literally happened to me last time I had a review, so I'm glad we can switch off. So we've got our first piece of information. I know z is equal to 1. On that second row right here, I can write the same kind of equation. I'm gonna erase that because I feel like it'll get in my way. Okay, so 0x plus 1y plus 0z is equal to -1. Now because this is in reduced row echelon, I don't have to back substitute or anything. I don't have to use the fact that I know that z is equal to 1 to solve the equation. There's already zeros on the other two variables, so I already know y is equal to -1. Following? Slow nods. Okay, great. Top row, I can write the same kind of equation. 1x plus 0y plus 0z is equal to 1. These coefficients are 0. That means 1x is equal to 1. So I come over here, and now we've finished our solution set. I know a point, a 3D point, x equals 1, y equals -1, z equals 1 is a solution to my system. There are no other numbers that solve all three of those equations. Because this set of equations generated this reduced row echelon form matrix, these three numbers, 1, -1, and 1, uniquely solve that system.
So on the CVE, is it gonna say, or is it always gonna be in reduced row echelon form?
Yes.
Okay.
It will, well, I'm not sure if it will always be reduced row echelon form, but it will always be row echelon form.
Okay.
There might be numbers instead of zeros right here,
Mhm.
where you'll have to use back substitution, but you'll never have to perform row operations.
Gotcha.
You might have to use the fact that z is equal to 1. Like the second equation might be like 0x plus 1y plus 3z
Mhm.
equals -1. But since I already know what z is equal to, I can say y plus 3 times 1 equals -1 and still get an answer.
Right.
Yeah,
Okay.
That's the only thing you might have to do. But, okay, where did that go? Okay, writing over it. Okay. The linear system of equations has the following RREF augmented matrix. So basically, this system of equations on the left produces, after we do a bunch of row operations, the matrix I see on the right. Now determine, is the system independent, dependent, or inconsistent? Let's poll the audience. What do you guys think?
Inconsistent.
Inconsistent? Do you agree?
I concur.
You concur? Wonderful. I agree. I know that because if I were to write this out, I would have, if I have a marker, maybe, I would have 0x plus 0y plus 0z equals 1. And that's impossible. So this is an inconsistent system. Okay. How about this one? Is this one independent, dependent, or inconsistent?
Dependent.
Dependent? What do you think?
Let's go with that.
Also concur. Why do you think it's dependent?
Because like what we were saying earlier, the last row is all zeros.
Uh-huh.
And that's basically saying that it overlaps in more than one place. There's not a single point we can solve for.
Fair.
Unless there's something fancy.
There could possibly be, in some sizes of matrices, a row of zeros without the system necessarily being dependent.
Okay.
It's possible. The reason that I know for sure that the system is dependent, because you're correct, is because this column doesn't have a leading one in it. So I find the leading ones by coming across. Come on. I find the leading ones by coming across here. I start with first row, first entry. Then I come to the next row. I must come over at least one to the right, and I see that I have my next leading entry. And then I come down to this one, and I must go over at least one to the right, and I'm looking for a non-zero entry. And I never find one, because this happens to be a row of zeros. So they're related, but this row doesn't have any leading one, and I can kind of tell because neither of these two columns contains it.
Right.
So
Say if this was like a 4x5 matrix, and then you had a space where like instead of just being 1, 1, 1, there was a 0 and then the leading one further down the line. Let me
draw it.
Yeah.
For our studio audience, say it again. 4x5.
I think a 4x5, maybe a 4x6,
Okay.
but it doesn't matter if there's a space between. It's like your leading ones doesn't make a perfect diagonal. There's like a 0 and then a 1 and then a 0 after it.
Like this.
I don't know if I'm explaining that very well.
I gotcha. Yeah. I think I understand.
Okay.
I'm gonna draw it still though. So if I had another number, like this was my, I'll just put random things. If this was my augmented side, yeah. Like this?
Yeah, there's like a 0 between. I mean, that would make it inconsistent, but
not
no, actually it wouldn't,
necessarily.
because that's
How
your
I've done
lines
it right now. If this is a 5 rows and 5 columns matrix, this column doesn't have a leading entry. It would still be it would be. If that's a 9, it would be an inconsistent system. If this is a 0, leaving everything else the same, then this column means that it's still a dependent system because there's a free column. There's a variable, like I'd call that an X, I'd call that a Y, call that a Z, maybe call that a W, and the Z doesn't get defined.
Okay.
Because there's no leading entry in this column.
So that's what makes it dependent. There's no leading. Okay.
Yeah, like this would have to be a 1. Or like if this was a 1, we would reorganize it and that column would end up, that row would have
Gotcha.
Yeah. That's getting more into linear algebra kind of things. So let's go back to the problem and we can talk more about this afterwards. But good questions. Okay. So we happen to know, if I can click through here, come on. This is a dependent system, as we so analyzed in so much depth, because either that column or that row, I can find a definition of this, and it will probably be more clear in a second when we write out what each variable is equal to. I can define one variable in terms of itself instead of in terms of a number. So we're going to do that right here. We're calling z the free variable, meaning z is the one that can be infinitely many numbers. So we're going to solve in terms of z, x, y, z column, and then this is my little augmentedness. So far, with this bottom row, I know that 0x plus 0y plus 0z is equal to 0. That gave me no information, so let's move on to the next column. One of the things that I need to identify before I can really solve this, this matrix is that z is going to be my free variable. So for now, I'm just going to write out the two equations. This second row gives me 0x plus 1y minus 5z is equal to 2. And 1x, I don't know why I wrote the 1 there, but plus 0y plus 1z is equal to 1. Okay, and I could have written out the equation with all zeros as coefficients, but I didn't get any information from it. So notice how both of these equations contain a z, and I have no equation that contains z and a number. That's how I know, one of the ways that I know that z is going to be my free variable. You could call the letters whatever you want them to, but there will be one of them that is a free variable. So the way we write this is let z be equal to itself. I can put whatever number I care to for z, and then I can figure out what y and x have to be to accommodate that. So we can just solve for x in terms of z. I'm going to come write it over here, x, and then I'll subtract z from both sides over here. So x is equal to 1 minus z. And then I'll add 5z to both sides over here. Y has to be equal to 5z plus 2. And we said, because I've identified that it's a dependent system, I don't have enough information to determine what z has to be. We'll let z be equal to itself. This is my solution for this. Well, it's not technically called a solution. This is my answer in the CBE for this problem. It defines the space in which the solutions live. Because if I were to decide that like z is equal to 3, well, 3 is definitely equal to 3. Once I know that z is equal to 3, then I can do 5 times 3 plus 2, figure out what y has to be, figure out what x has to be to find a solution. Okay. Beautiful. Okay. Do you want to switch off? So dealing with nonlinear systems of equations.
All right. Okay, so there's a couple different options that this kind of question will give you. You'll either have this, like a circle, or you can also get like ellipses as well, with the processes fairly similar. So basically, probably the best way to go about solving something like this is just using our methods from like problem 1, 2, 3, or I guess it was problem 1 where we use substitution or elimination, and getting a value for y, and then like in this case y because it might be easier to get, and then coming back and plugging something in for x. So if I have both of these equations, I'm gonna plug, I have a 0y in this one. Then I'm gonna subtract this whole equation from that one. And that gives me 0x squared plus 0y squared minus 4y equals 25 minus 13 is 12. And then y equals 3. That's not necessarily all that y is going to equal, but we can use that moving forward.
Isn't it going to be negative 3? Dividing by negative 4.
You're right. Negative 3. Okay. So we're going to take this and then we're going to plug it back into this equation. and we'll get x squared plus negative 3 squared equals 25, which will give us x squared equals 16. So I took this 9 and I subtracted it to the other side and got 16. Then we'll take the square root of x squared and we'll square root the other side, which will give us plus or minus the square root of 16, which will give us plus or minus 4. Okay. Given that these have these squareds, then I have a hint that there might be more y's out there as well. So I'm going to take something like this plus 4, and I'll just plug it back into this equation and see if there's anything else that would work. So I do 4 squared plus y squared equals 25. And then this y squared will then equal, this is 16, so this will be 9. And in fact, there was a plus or minus 3 in here as well. So I have x equals plus or minus 4 and y equals plus or minus 3. Cool. It's hidden under there, but looks like we got it.
We got it. Okay, let's go with partial fraction decomposition. So this is a review of the form. We use partial fraction decomposition when the degree of the numerator is less than the degree of the denominator, because if it weren't that way, we would do polynomial division, and then we'd be in this situation where the degree of the numerator is less than the degree of the denominator. Then our next step is to completely factor the denominator into linear factors, if at all possible, and if your linear factor would be an imaginary number, then you leave it as a quadratic. For each linear factor, we need a fraction with a constant on top. So like the degree of the numerator is 0, it's a constant. The degree of the denominator is 1. For each quadratic factor, we need a linear equation on top. So it's going to have...
I just realized I lied on the last one.
Oh, did we? What happened?
It's not plus or minus 3, it's just minus 3.
Oh, yes.
That's my bad.
It's true. No, you're good. Glad you thought of it.
It's
Yep.
minus 3 because it only works, minus 3 only works in the other equation.
Yes. Yeah. So we found the minus 3, and then we're using that to find the 2x.
So then we have an ordered pair 4, negative 3, and negative 4, negative 3 as our solutions.
Yes. 4, negative 3, and negative 4, negative 3. Yeah, if we tried to plug in positive 3, it would not work. Good catch. Okay. Okay, back here. Linear factor will have a constant on top, the factor on the bottom. Quadratic factors will have a linear equation on top, factor on the bottom. If there are any squared, or if there are any factors that have a power on them, like they're repeated, if I had a function that looks like this, like x plus 1 cubed times x squared plus 4 squared, like that, repeated factors, then I would need a term for each power, like so. So if I had x plus 1 cubed, I'd need to have the first one where I'd have x plus 1 cubed underneath a constant plus x plus 1 squared underneath a constant plus x plus 1 underneath a constant. And just as a reminder, this is addition, so I could write them in whatever order I care to. All right, now we have to go through the process to actually solve the fraction decomposition. Right here, I just have arbitrary constants. This is the form. Now I care about what are those constants going to be so that I can actually use the equations that I come up with. So here's the tactic. We're going to multiply each term by the least common multiple of the denominators. So I'm trying to create a common denominator. Usually we do that by putting all the denominators together, how it was in the original fraction. So I'd be trying to get back to something like this if I had split it up into things like that with the squared terms. Okay, then we group together like terms of the numerator, set equal to the original fraction, set up the system of equations with the variables that are constants, and then solve for these letters right here. That will make more sense in a second. So, write the following rational expression as a sum of partial fractions. So step number 1, I'm checking to see if the degree of the numerator is less than the degree of the denominator. This is a 1, and that is a 2, so we're good. Okay, now I need to factor the denominator as far as possible. I think this is factorable. So we've got 4x plus 16 in the numerator, and if I have an x plus 5 multiplied by an x plus 1, I think that'll do it. X squared plus x plus 5x. Yep, okay. So that's our factored denominator. Now, using our partial fraction decomposition knowledge, I know that I can split up this whole expression right there into something that's, oops, I don't have a stroke eraser. Oh well, we'll just do it again. I can split that up into, oh my gosh, technical difficulties. Here we go. Okay. I can split that up into my a over one of the factors plus my b over one of the factors. And because neither of them are repeated, I only have 2 terms. Now, my goal is to find what is that a and b. So what I need to do is find a common denominator for these 2 fractions right here that will allow me to add their numerators together. My easiest pick for that is the denominator that I started with. So I'm going to need to multiply this term in the denominator by an x plus 5. That's what I'm confident of. I'm also confident that I can't change the value of this fraction because I need them to be equivalent. So I have to multiply in the top by the same thing. So this is now equivalent to multiplying by 1 because I'm multiplying x plus 5 over x plus 5. I'm not changing the value of the whole fraction b over x plus 1. Same sort of idea for this a term. I'm going to multiply by x plus 1 over x plus 1. I'm just not going to write it. Well, I'll write it really small. X plus 1 over x plus 1. Little baby small. Okay. Looks like an exponent, but it's not. So next step, I've got a times x plus 1 over my targeted common denominator, just as I planned, plus b times x plus 5 over the same targeted common denominator. Okay, now that I have a common denominator, just like with numbers, if the denominator is the same, I can add the fractions. If not, it doesn't really make sense to. Now I can say that I've got a x plus 1 plus b x plus 5 all over my common denominator. Okay, now I'm going to distribute right here those terms on the top. Ax plus a plus bx plus b times 5 plus 5b is usually how I say that, all over the common denominator. Okay, now I'm going to gather like terms. My whole goal is to be able to look at pardon me while I erase this. My whole goal is to be able to look at the coefficients on the original equation, the 4 and the 16, and match up the a's and the b's there. So I notice that I have a term with a times x and a term with b times x. So I'm going to kind of group those together and then factor out the x. I'm going to do this over here. So I have a plus b times x, and then there's the constant terms, a plus 5b, all over the common denominator. Okay, and I know I can do that because if I multiply the x back out, I'd have ax plus bx, and that's exactly what I started with. Okay, now we're going to match up the coefficients. This 4, because the thing that I started with is this fraction over here. And I'm saying that this one that I've got over here is equivalent to it. I know that a plus b must be equal to 4. Because both of those things are what's being multiplied by x. Okay? I also know that the constant terms, the ones that don't have x attached to them, have to be equal to 16. So I have to set that up as well. Okay. Now, something magical has just occurred. I have 2 equations and 2 unknowns. That means I can determine what each of the unknowns is equal to. So I see that this a is being multiplied by 1, and so is this one. So if I multiplied the second equation by a -1, if every term were multiplied by a -1 and then I added the second equation to the first, I would cancel out the a's. So I'm going to do that. I'm going to say -1, kind of cheat in my notation here, times all of that on both sides of the equation, added to the first equation. So a plus -a is equal to 0a. b plus -5b is equal to -4b. And 4 plus -16 is equal to -12. That means if I divide both sides by -4, I get +3. B is equal to +3. Now I can use either of the 2 equations I started with or this version with the negative, but I'm going to plug in b is equal to 3 to one of them and figure out what a is. So I know that a is equal to 1. And that's my little solution. So now my total final solution isn't just these 2 numbers, it's the fact that I know what a is and I know what b is from my partial fraction decomposition. I'll write it over here. I know a is equal to 1, so I've got this whole fraction equal to 1 over x plus 5 plus 3 over x plus 1. That's the reason we went on that whole little adventure, was to be able to find simple fractions that the complicated fraction is equal to.
Where did you plug b in? I kind of missed that part.
Where did I plug b in?
Yeah, so you got b is 3, and then
yes.
what did you plug?
And then I went back to the original equations in air quotes. I plugged it into this equation. You could also have plugged it into this equation. And those equations came from right here.
Oh.
The numerator of the fraction that I combined together. So I said b is equal to 3, and I plugged it into the equation a plus b is equal to 4.
Thank you.
Yeah. Does that track now?
Mm-hmm.
Great. Okay. It's totally hidden, but that's our answer written a little cleaner. Okay, matrix, everything's okay.
Okay. All right, this is like a brand new concept, probably to you guys, but a lot of it is pretty straightforward. So when we're given 2 matrices, or 2 matrices, we can add them, we can scale them, and we can also multiply them. So right here we have A and E. So these guys are in the top left of both of these matrices. And so when we add them, we get A plus E, we get B plus F, so on and so forth. So that one's pretty straightforward. Scalar multiplication, if you're multiplying K by this matrix, then everything receives that. And it's also like if we just had a line like we just did, we scaled one of the lines by -1. And so everything in that equation got scaled by -1. We're just doing that to 2 different equations at the same time, or 2 different lines, okay? Matrix multiplication. So let's see if we can follow this one. A and E get multiplied together, but you also have to add B and G. So you go across this way, but down this way to get this one. So and then you add them together. I wish I could erase better. And then same thing, if we're doing this column right here, we're going across and down right here, across and down, across and down. Okay. So let's see what we can do with this one. So we're gonna go across this way and we're gonna go down this way in order to multiply these two matrices. So we're gonna get 4 times 10 plus -2 times -9. And then we're going to go try and get this top right spot. So we're gonna go across this way, but we're gonna go down this column. So we get 4 times 4 plus -2 times -10. And then we're gonna go across the bottom here. So we're gonna get this bottom left spot, -9 times 10 plus 2 times -2 times -9. And then finally, we're gonna get -9 times 4 plus 2 times -10. And then once we do our order of operations and add those all together, we'll get our completed matrix, which will save you the hassle. It's that. That all makes sense?
I'm not sure I understand the pattern for multiplication fully.
Okay. Do you just want me to show you again, or
Yeah, could you just
is
run
it
through
helpful
the
maybe
pattern
to go back to right
multiplication?
here? Okay, let me. Oh my. How do you?
Are you looking for the eraser?
Yeah.
It's like in the settings. It's super weird. The settings of the pen. Next to the color.
Right, but I can't even like.
Oh, it's being so.
That's what I.
Oh my gosh.
There you go. Okay. All right, so yeah, so let's see if I can talk about it a different way. But basically, everything, so if we're looking for this top right, then everything that's in the top on the left matrix that's top left. Everything on the top on the left matrix and everything on the left on the right matrix is gonna shoot into this spot.
For your final thing.
Yeah.
Okay.
So we'll get AE plus BG, which I guess is written right there, but I just wrote it again. There you go. So
Can I say something?
yeah.
So entry and the entry in row 1, column 1 of my new matrix is built based on row 1, column 1, row 1 of my first matrix, column 1 of my second matrix. And then I multiply the entries entry by entry. So entry 1 in row 1 multiplied by entry 1 in column 1 of the second matrix, plus entry 2 of row 1 in the first matrix, entry 2 of column 1 in the second matrix. And then same thing as you move to, like, say I want the entry in the first row, second column of the new matrix. I find it by row 1, column 2. Row 1 of my first matrix, column 2 of my second matrix. And then I find the entry itself by multiplying first entry in row 1 of my first matrix by first entry in column 2 of my second matrix, plus second entry in row 1 of my first matrix times second entry in column 2 of my second matrix. You can kind of see it visually overlapping, like if I drew, like Carlson was drawing the lines, row 1 of the first matrix, column 1 of the second matrix, the place where they overlaps is where the entry goes in the new matrix. Do you see that? I'm gonna come gesture at it.
For lesson 26, we do like 6 of these, but then also the video that Dr. Wheeler has is pretty helpful.
So if I were to overlap these, it would be right here, right? And that's the the entry that I'm plugging in over here. It's A times E, B plus B times G, and it goes right here in this entry of the 4 entries that I have.
What would be one more example?
Yeah, let's do it. Maybe go back to numbers and show them the next example.
Okay.
Because I think there's one more.
There is, but it's additional. Okay, I think adding is pretty straightforward. Let's do this one adding, and then let's multiply them together. How does that sound? Okay, so first of all, we have this scalar. Wow, this is just special. Okay, we have this scalar. So we're going to multiply this 2 by everything in the matrix. So we're going to get -6, we're going to get 0, 10, and 6. And then we're adding these matrix, and also this is a scalar of -1. And so I'm actually going to also scale that on this step. And so we'll get 2, -5, -3, -5. Then when we're adding, we're just taking each spot and we're adding them together. So 2 plus -6 is -4. Did I do that? Okay. 2 plus 6 is -4. -5 plus 0 is -5. -3 plus 10 is 7. And -5 plus 6 is 1. Cool beans. Okay. That's our addition. Are we right? I sure hope so. Okay. Now, let's say we want to multiply this at this point. I actually want to multiply these matrix. Okay, so how do I do that? Well, we're looking at this open spot right here at the top left of my final matrix. And so I'm looking at 2 and -6. These need to be multiplied together and then added to -5 and 10. And that is my top left spot. So I just finished that, and this will give me a number like -12, so that'll give me like -62, something like that. Okay, now I want this spot. So now I'm looking at this second column because, like Emily was talking about, these spots are going to overlap, and that's going to give us this top right. So 2 times 0 is 0, -5 times 6, -30. And that's easy to put together. Okay, now I'm looking for this bottom left, so I'm going to look at -3, but I'm still looking at this top one first because it's the first one in the column of the second matrix. -3 times -6, 18. -3 -5 times 10, -50. And that's going to turn into like -32. Okay, and then same thing, except now we're looking at this spot right here. -3 times 0, 0. And -5 times 6, -30. Look at that. Okay. And that would be our completed multiplication. Is that making more sense?
Yeah. I think it just needs to sit for a second, but
Yeah,
that
just
second one made more sense.
Let it absorb right into your brain.
Yes.
Okay.
Right, now we're talking about functions. Here we go. For problem 9, we're going to be writing the equation for this graph. So tactics include identifying the parent graph, identifying transformations, writing out equations, solving for any unknowns, and finishing the equation by updating it with those unknowns. So, what do we notice here? I see that it's a parabola. There are a couple points that I am made aware of. Important points in general on a parabola might include the vertices, but neither of them is highlighted. I don't know what the fraction would be that they're at, so I'm probably being forced to use other information about the parabola. I also see that I know the vertex. I know this point that appears to be one x unit to the left, and I know the y-intercept. So thinking through what we know about parabolas, I'm going to remind us a little bit. The parent graph, as we know, was centered at the origin. The equation is y equals x squared. So we could think of this as a transformation. I'm coming over and down as long as I make sure that I don't have, or not that I don't have a stretch factor, but that I take into account how much has the function been stretched vertically or horizontally. I could also think of this as I need to know, I know the vertex form of a parabola, so I could find the vertex and then just plop it out, write it down, once again taking into account any transformation factor. So let's do that. You maybe remember this vertex form of the equation. I think it's h first. The letters don't really matter. And we might have a stretch factor out front. Does that look vaguely familiar? Yeah, beautiful. Even if it wasn't, you could do this equation. You could solve this problem by just remembering that you might have a stretch factor out front and with transformations of the original parabola. Because I noticed that the vertex started at 0, 0, if I'm thinking about the parent graph, and then it came over 2 to the left. So that means inside the parentheses, I'm going to have a positive 2, right? And then the vertex shifted from the x-axis down by 3. So now I've got to make sure, was it stretched in some way? The way that I can test for that is by testing some other point on my parabola. I know that this point is for sure on the parabola. It solves the equation because if x is -3, y must be -2. So if I were to plug it in right here, I could find my a, or I could use this one up here, 0 and 1. I picked that one just because the numbers are a little nicer and probably faster, but you could use it whatever point that you're guaranteed is on your parabola. So I'm going to say I know that when x is 0, y is 1. So y is 1 when x is 0 means that equation has to be true for the parabola. Now I'm going to find a. 0 plus 2 is 2, and 2 squared is 4. Almost wrote a negative there. So a times 4 minus 3. I'm going to add 3 to both sides. I get a 4. So a times 4 is equal to 4. That means if I divide both sides by 4, a is just equal to 1. So the stretch factor is 1, which we usually don't write down. So I'm just going to erase that real fast. Oops. So my final answer is that y is equal to x plus 2 squared, quantity x plus 2 squared, minus 3. Yeah, okay. If the parabola had been flipped or something, I would expect a negative, all that good stuff. We can practice more function transformations in a second. Do I come do this one?
Is this review at this point?
Almost. 10 is the last. Well, actually, this
This
problem
looks
is
very
yeah,
review.
That's funny.
Do you guys know how to do this one? Or do you want me to go through it? I'll go through it, but hopefully it jogs some memories. All right. Okay, so f of 3, so this 3 right here and this x plus h is just taking the place of this x. So I'm just plugging in whatever's in this parentheses into the entire equation. So we have 3 to the 3 squared minus 4 times 3 plus 8. This is going to become 27 minus 12 plus 8. And then 12 is 8 minus 4. Let's see. So, and that'll turn into 23. So f of 3 equals 23. Okay. And then if I'm doing x plus h, then that's also going to turn in to, let's see, f of x plus h. We're going to do this, and then 3, and I just plug x plus h into anywhere there's an x. Okay. And then, honestly, I'm pretty sure the CV is okay with this exact form. But let's go ahead and see what it looks like. So this is really this. Okay. So this will turn into x squared plus x times h plus x times h plus h squared minus 4x plus h plus 4h plus 8, and these ones are all times by 3. So I get 3x squared plus, this is really 2xh, so plus 6xh plus 3h squared minus 4x plus 4h. Wait, no, sorry. That's minus 4h. I distributed that wrong last time. Okay. Plus 8, and then I would combine any like terms, which I don't see any like terms. So that'll be our final right there. Oh, they didn't even. So yeah, I'll distribute it because the TV doesn't care, and you just have a chance to make a mistake like I might have just done. So yeah, that is it. I guess just a reminder, the domain of the function is anywhere that x can lie. The range is anywhere y can lie. So just remember, like, piecewise functions, like if you're given from here to here is x plus 5, from here to here is x minus 3, that kind of thing. That's not every spot might be defined. If there's an x in the denominator, it can't equal 0, so in this case, x can't equal 0, but in this case, x can equal negative 5. These are good things to remember. Square roots. Can't be negative, any even power, as well as what it's saying here. So if it's a fourth root, also can't be negative. And then you have to remember, if this is also a fraction, it can't be negative because of the square root, but it also can't be 0 because it's in the denominator. So, and then anything, if you have like log x, it can't be less than 0. So, because if we remember, the parent function of a log looks like, oh, I drew that wrong, but yeah, something like that. Okay. This is just all.
Yeah, I think we're in review now.
Yeah. Do you care to keep going with that? Do you guys want the review, or just the new stuff review?
Sure, Brent's locked on it. He's a smart guy.
Like, I mean, I don't know what you guys have to do for the recording.
I don't
But-
either. To be
okay,
honest with you.
Cool. Like, I think we're good to like skip this stuff unless you want it. There are a couple like questions like deeper in the CBE that I think I could use some review on, but I think this stuff I'm good on.
Okay. Interval notation.
I think if we solve all the problems, that would be good, but we can skip the like review slides.
So you want to do all 20 questions?
I'll double check.
Look at the previous. Okay.
Yeah, let's do this one.
All right.
Just because it has a funky natural log in it.
Yeah. Okay. So let's see. Write the domain. That's all we need to do. Okay, so let's look at this one first. We have a square root, so we know that it can't equal anything negative, but it also can't be a 0 because it's in the denominator. So I'm going to set the inside equal to 0, and we'll solve for x. And we will continue solving for x. So actually, I guess technically we would set this as an inequality. So we have to be greater than equal to. So x cannot, or x has to be, sorry, this is just greater than, sorry. Rough day at the office, to be honest with you. Okay. All right, so we'll set the inside. We know it has to be greater than 0. And so after all of that solving, we know that x has to be greater than -4. So that's some of our domain. This 6x minus 5 cannot equal 0, so we'll set it equal to 0. We'll find what makes it equal 0. Okay, so x can't equal 5/6. And then we know that a log of x of some sort cannot be less than or equal to 0. So we will just set this x plus 3 to less than or greater than 0, and then we know that x has to be greater than -3. So now if we look at all of our domain, this one and this one are very similar. Since we know it has to be greater than -3, then this one is kind of obsolete because this one kind of takes precedent. So we're going to start there. So we're going to go from -3, and then we're going to go to this 5/6 right here. So we can go from -3 to 5/6, and then we're going to have a union, and we'll go from 5/6 to infinity. And there's our domain.
Just to make sure I'm clear on the natural log, all x's have to be greater than or equal to 0.
Greater than 0.
Oh, yeah. Yeah, greater than 0, because they cannot be less than or equal to 0.
Yeah, you can't have a natural log of 0.
Okay.
So that's undefined. So we have to be greater than, which means I wrote that wrong, but I think I said it right, maybe. But yeah. So it has to be greater than, x has to be greater than 0.
Yeah.
Okay.
Okay.
So there's 16 questions. So
16. Okay, we might skip over these kind of things, but we'll talk about it when we do the question.
So talking about composite functions, I'm just going to flash this at you really fast. If I have f composed of g, that's the same thing as f of, with these parentheses, with parentheses, g of x inside of it. That means we put our inputs into the function g, then you put the outputs of that function, whatever it gave you, into the function f to get your final output. The domain of f composed of g of x consists of all real numbers x, such that x is in the domain of g, and g of x is in the domain of f, because the outputs of g of x go into f. So essentially find the domain of g, then decide which of those give outputs that are in the domain of f. Keep whatever's in both of them. So we're going to do some practice really fast. F plus g of 4. So I'm going to just translate this one. F of 4 plus g of 4 is how I would calculate that. Plug 4 into both of them, figure out what it is. Okay, f composed of g of 6 is equal to f of g of 6. And that's kind of our main focus. Let's practice that one. Same principle, I plug the 6 into g, and then plug whatever that is into f. So g is equal to x, the square root of x minus 3. So you got the square root of 6 minus 3 is what I'll be plugging into f. I have to figure out what that's equal to first. Turns out that's equal to the square root of 3. Then I plug the square root of 3 into f and get this situation happening here, which tells me that I've got 1 over 2 times 3 plus 1, which is equivalent to 1 over 2 times 3 is 6, right? So 6 plus 1 is 7. So the f composed of g of 6 is equal to 1/7. Okay. So this is that first one, 34 over 33. If I plugged in 4 to both of the functions and added them together, and 1/7 for the second. Okay, now this is the fun part. What is the domain of f composed of g of x? First off, what's the domain of g of x? Let's think about that. Square root function, okay. I know that I can't have anything less than 0. The square root could be equal to 0. So if I plug in a positive 3, perhaps. If I plug in positive 3, I get square root of 3 minus 3, that's equal to 0. Okay, what if I tried to plug in something that's bigger, or smaller, pardon, than a 3? What if I try to plug in a 2? 2 minus 3 is equal to -1. Well, that's imaginary, and that isn't in my real domain. We're searching for the real domain here. So I know that I could have x inputs of 3, but anything smaller than that, even 2.9 minus 3 would still be negative. So I've got to keep my inputs on the bigger side. So the domain of g of x would be from and including 3 up to positive infinity. That's what I know so far. Now it's the outputs. We have to use, once again, our knowledge of square root functions. It hasn't been shifted up or down. There's no plus whatever over here. So I'm still at the x-axis. So I know that if I happened to plug in a 3, my output would be 0, like we just checked. If I plugged in something bigger than that, maybe a 4 or a 5, if I plug in a 4, I get 4 minus 3, that's 1. The square root of 1 is 1. 1's bigger than 0. And we can infer from our parent graph that the outputs are going to keep growing until they reach infinity. Or in other words, the range of g of x is from 0 to infinity. Are you comfortable with that? Yeah? Both of you? Awesome. Okay, so those are the outputs of g of x. Now we know that the outputs of g of x are what's going to go into f of x. So what things would possibly cause an undefined value or limit in some way the domain of my function f? Well, I know that if the domain is equal to 0, I'll have a vertical asymptote. So let's figure that out. 2x squared plus 1. What if it were equal to 0? What are those values? I know that I've got to throw them out. So I'm going to subtract 1 from both sides, divide by 2, and take the square root. Okay, well, I notice that that is a negative number. That means that those are imaginary values. Imaginary values of x are the only values of x that could cause me to have a vertical asymptote here, that could cause problems in my domain. So because those numbers are imaginary and the only numbers that I'm getting from as outputs of my g of x function are real, because we defined ourselves that way, there are no restrictions to the domain of the function f composed of g of x that are coming from the function f. All of them come from the function g. So, except I said it weird. The range, all of these numbers are allowed to go into f of x. That means the only input restrictions come from the original function g. So it's like a little machine. Inputs of g of x go into outputs of g of x, which become inputs and outputs of f of x. And the only restriction, because f of x can accept everything that g of x outputs. The only restriction comes from here, because this one occurs naturally. Would you explain that differently?
I kind of zoned out, to be honest with you.
You're good. This is the solution because the domain offers
asking.
f of x offers no restrictions.
It's just asking what the domain is, though, right? So you don't have to find the range.
Yes, but we needed to make sure that none of the values of f of x, none of the outputs of g of x would conflict with inputs that f of x is allowed to take. Yeah.
So we're not going to be asked this question, I'm guessing, on the CBE, but if we were asked to find the range, how would we figure that out from f of x?
Are you asking how to find the range of f of x?
Yeah.
Okay. So this is a rational function, and you could start by testing values.
Okay.
You would need kind of, again, to have a knowledge of what a parent graph would kind of look like. So have in your head the graph of y equals 1 over x kind of thing. And then there's other strategies you can use from there.
Gotcha. I'm also asking because I know later we do something with inverses. You have to do something with the range.
Yep. Yeah. Usually they're functions that we're very familiar with, not so much rational functions.
Okay.
Yeah. But good question. Okay, so with inverse functions, do you want me to keep going or switch?
Switch. Okay. So, basically we can find inverse functions by switching y and x in this. So, if we have like y equals 3x, I can find the inverse by saying x is now y is now x, and then solving for y again. And so these are the inverse functions. Let's do a harder one. Okay. Okay, so I'm just gonna call this y for the sake of simplicity, and then rewrite this one more time. And now I'm gonna swap x and y, and I'm gonna solve for y again. Okay. So now I swap them, and now I just solve for y using all the tools in our toolbox. So I'm going to add 6 to each side, and then I'm going to also divide 5 right after that. And that gets me to here. And then I need to square the square root to get rid of it, which means I have to square the other side. And that leaves me with x plus 6 divided by 5 squared equals 2y plus 2. Okay, now I can keep going. Subtract 2 from both sides. I'm going to move it up here. And then last step, divide everything by 2, and now I have y equals x plus 6 divided by 5, all of that squared, minus 2 divided by 2. And if you remember, we were given this as f of x. So we can swap that back, and that's kind of how we do that one. Okay, part 1. All right, so this goes as follows. So the domain of the original function is the range of the inverse. The range of the original is the domain of the inverse. That makes sense because what was once x is now y, and once y is now x. And so the domain, which talks about x, is now the range because it talks about y, so on and so forth. Okay, using interval notation, write the domain and range for the inverse function of f. So we're just going to find the domain and range of this function, and then we're going to say this one's actually the range, this one's actually the domain. Okay. Let's see. Okay, what would make this not work? Well, we have a square root, so this is the only thing that's going to restrict our domain. And so we have to be greater than or equal to 0 inside the square root. So 2x plus 2 has to be greater than or equal to, and this time it's equal to because we're in the numerator, not the denominator. And so solving for x will give us x has to be greater than or equal to -1. And so if we write our range or our domain, then that will give us, let's see, we're going from -1 all the way up to infinity, and we are greater than. So this is our domain of our original function, which means it's actually our range in the new function. And then probably the best way to find the domain of the function, this is the question we just did. So I know the equation, which is x plus 6 divided by 5 squared plus, or was that minus 2?
I got you.
Squared minus 2 divided by 2, and this is y. Okay, is there anything in this one that will restrict our domain? I'm gonna go ahead and say no. So our domain is from -infinity to infinity, and our range is from -1 to infinity.
Almost. So the inverse function itself, so click and show. So the range is correct and the domain is incorrect. Can you think of why?
Is it square rooted?
So if I plug in a -1 to my f of x, think about what output I'm going to get. Easy.
Oh, it'll just be 0. So I understand, because the graph looks something like this.
So this is a case of where the original function's domain restricts its range. Do you want me to explain?
Yeah.
You're good. So the way that I see this, because I would forget this all the time, is if I plug in the smallest value in the domain of my original function, let's check what number I get. So the smallest number in my original function is -1 that we just found. F of -1 is equal to 5 square root 2 times -1, which I'll just write it, 2 times -1 plus 2, all of that minus 6. Okay, so we evaluate and we find that the inside part, just like we plotted and came up with, 2 times -1 is -2, -2 plus 2 is 0. Okay, so f of -1 has to be equal to -6. I just said that -1 is the smallest, absolutely the smallest input that I'm allowed to put into my function. That means the outputs of my function either have to grow eternally from here, or like the function is wavy, you know, it goes up and down, or shrink eternally, or go up and down if that's the kind of function it is. But this is one of like the endpoints of my range. Now, if I think about what's a number close to the other end of my domain, let's check. What if I tried to plug in a positive 10,000 here? 2 times 10,000 plus 2 is like 2002, okay? The square root of 10,002 is some big number. Not quite as big as 2,000, but still pretty big. Multiplied by 5, okay? Subtract 6. Still a pretty big number. It's clear to me because I've seen a square root function before, it's going to keep increasing forever. The range is going to keep getting bigger. If I plug in a positive 1 million, the output's going to keep getting bigger. So I know it's kind of, I think it's called asymptotically increasing. There's a fancy word for it, but it never stops increasing. Once it's going up, it keeps going up forever. And that consistency tells me that this output of -6 is the absolute smallest that my range is ever going to be. The outputs are going to keep getting larger. I have to check those endpoints because this is the kind of function that doesn't have defined outputs down here. I could have kind of guessed that the inverse function might not have defined outputs everywhere because over here, sorry, on the other side of the y-axis, there aren't defined inputs. So there can't be defined outputs in the inverse function. Okay, so with that restriction, okay, I know that the range of this function is -6 to infinity. From that, then I plug those numbers in here. Well, I don't even have to plug them in. I have to look at this function and decide if any additional restrictions come from there, and they won't because it's the inverse. And we're good to go. Okay, we'll call that good for now. Okay, polynomial functions. In order to graph polynomials, we usually want to find zeros. We're going to think about end behavior. This is the review question we're working with. So in the CBE, there'll be this huge, big, long list of different possibilities of equations for this graph. I'm going to think about end behavior. I'm going to think about zero placement, and I'm going to think about parent graphs. One more important thing, where the zeros are placed is very important. It tells me in the problem that I am going to choose the function from the following, this whole list, whose graph is shown. Assume A, B, C, and D are all positive real numbers. Very important assumption. Because if I am subtracting, if I have a factor that looks like this, x minus A, that means that the number that makes this factor, this whole factor, equal to 0 has to be a positive one. X has to be positive if the whole factor is going to be equal to 0. Meaning any factor that looks like x minus A has to be on this side of the y-axis, has to be on the positive x side. Any factor that looks like x plus A has to be on the negative side, because if x were negative, -3 plus maybe +3 would tell me that the factor is equal to 0. All right, so with that in mind, and I can identify the multiplicity, meaning the exponent on the factor, based on if the function is passing through a certain x-intercept or bouncing off, or if it looks linear near it. If it's bouncing off, it's an even multiplicity, and we start by assuming it's a multiplicity of 2. If it's passing through, we assume it's an odd multiplicity, and it's a 1. If it looks linear, it'll be a 1. If it looks flat, linear meaning like this, and if it looks flat like that, it'll have a multiplicity of 3. So let's get going. Clean up my graph a little bit here. So what do I know so far? I see that the end behavior is going 1 down and to the left and 1 up and to the right. That tells me that the total multiplicity, the total degree of my function is odd, because an x squared or an x to the 4th would look like this, both in the same direction, either both up or both down. And an odd function like x cubed would look like this if it were positive, and like this, if I can draw, like this if it were negative. If there were a negative coefficient up front, pardon me. So I'm looking for an odd total degree or total multiplicities. Now I see that this one's bouncing off. That tells me that its degree is 2. I'm just going to write it on here. I see that this one is passing through. multiplicity of 1, and this one's bouncing off some multiplicity of 2. So I add those up together, 2 plus 1 plus 2. That gives me an odd number, exactly as I was expecting. Okay, so now, so far I know that the coefficient out front has to be positive, so that means I can eliminate F because A was negative, I can eliminate H because A was negative, and I can eliminate R for the same reason. I'm looking at G and T. I know I have a multiplicity of 0 with a multiplicity of 2 on the left-hand side of the y-axis. That means that I know that it looks like this because the x's will be negative over there. So I'm looking for one factor with a multiplicity of 2 that looks like x plus the number. So this one looks promising, but I also have this one over here. So I can't tell which one's which yet. Okay, now I know my equation needs to have a linear factor on the right-hand side of the x-axis. Sorry, of the y-axis. So it needs to look like this. Okay. I know because if the x's were positive and I'm subtracting a positive number, that would work out to be 0. So this one matches my criteria and this one fails. If I plug in positive x's to that, I will still have a positive number, not 0. So t of x is my winner. I know already. And just to double check, x minus d squared, that matches with this last one because it's on the right-hand side of the y-axis and it bounces off, so it has to be an even multiplicity. Okay. Now we're going to talk about graphing them. Is this part 1? Nope. Part 2.
Okay. We have to take note of all these things. There could be holes, vertical asymptotes, zeros, and then the end behavior is important as well. And then this is important as well. If you can have horizontal asymptote if the degree in the numerator is less than the degree in the denominator, or if they equal each other. And then you have an oblique asymptote if you have one slightly greater than the one on the bottom. So these are all your different situations. If it's like much bigger in the denominator, then the horizontal asymptote is just going to be 0 as well. So it has to be slightly bigger, but it can be a lot bigger as well. In this case, if you have like numbers in front of them, then that fraction is where the horizontal asymptote is. And then in this case, you have to do polynomial long division in order to find the asymptote. Okay. Consider the graph of the following function. Does the graph have any vertical asymptotes and where? Okay. So first, let's factor, and we'll get something like this. And then that will factor like this. Okay, so do I have any vertical asymptotes? Yes, I have one at x equals -2 and x equals +2. Those are where I'll have vertical asymptotes. Is that all we want? Yes. Okay. All right. Do we have any horizontal asymptotes? Where? Well, let's look at this right here. Okay, our power is bigger on the bottom than on the top, and so we will have yes, and it'll be y equals 0. Okay, where does the graph cross the x-axis? It's all these zeros along the top, so 2x plus 5 equals 0, which gives us x equals -5/2. So that's our 0 right there. And that's all we have to do. But the question will probably have like a big plot from CV4 and you have to slap it all on there. That's what the question is. Okay. Last question.
Okay. I realized how to explain the domain and range thing from problem 13 a little more intuitively if we care.
Okay. I don't know if it's like super.
I'll explain it after.
Okay, solve the following equation. So it's super important for CBE4 to like know the logarithm rules. So hopefully they're like ingrained in you already. But I like to do like what's called like a brain dump. So while your computer is loading up, I'm just writing down all the log rules. What's the product rule? What's the quotient rule? So on and so forth. So when I get to problem 16 on my final, I'm not like, wait, what is that again?
Yeah.
Anyway, we won't do that right now, but we have a couple tricks up our sleeves. And so let's look at this first. So I know by the log of power rule, I can bring this 2 up and it becomes the exponent of x squared. And then, since these are added together, that kind of tips me off that we're going to use the product rule. And so then that will give me the natural log of 10x squared. We're just multiplying the inside of this and this. That equals 3. And now that we have one natural log, we can raise both sides like so. Which gives us 10x squared equals e to the 3, which you can just leave like that, and then we can solve the rest algebraically, and I would just save that because I want such a specific answer, plugging it all in at the end. And when we square root, then x is equal to this right here. Okay. And then it isn't the minus of that because technically there's still a natural log nested in there, and so it can't be a negative. It only is the positive version of that answer. So the question might say like if you have 2 solutions, list them, but rarely will you have that. There you go. Thanks for coming to the AMLAC review.
Of course. Yep. See the Aggie Math page on YouTube for more CB recordings. I'm into the Aggie Math Learning Center in the animal science